They give us the whole diagram. That's all we're going to need to solve this. We will find the shear strain at point A, gamma sub A. Then we have our undeformed shape, and then we load it up, and we want to see what the new measurements are. When it's deformed, point A will move to the right by 3 millimeters. All the units are in millimeters here. I don't want to crowd it too much. And it moves in the positive y direction by 2 millimeters. To go from A to A prime. Point B moves to the right by 5 and up by 4. And point D remains stationary. Point C will move 2 and 2, although for this problem that won't really matter. What we're looking for now is, originally AB and AD were perpendicular to each other. Now A prime, B prime, and AD prime are some non-90 degree angle that we're going to call theta prime. We know from the previous one that to calculate angle A, or the shear strain at A, is going to be pi over 2 minus theta prime, I'll call it theta prime A. Pi over 2 is just a number. What we need to find is theta prime A in order to calculate the shear strain at point A. How can we find the angle between two lines? Right, we can use the dot product. We didn't really use it for the angle purpose then, but right now we can. We can find the angle between two vectors, really, by using the dot product, because in the dot product, we know that, just for example, A dot B, well, I'll write it out the way that I'm going to use it here. A prime B prime dot A prime D prime is going to equal their magnitude times the cosine of the angle between them. If I dot these two vectors, that's equal to the magnitudes, the product of their magnitudes, times the cosine of the angle between them. So I want to go from A prime to B prime. How did we do that in EMCH 211? I can take B prime minus A prime, and that gives me, how do I go position vector A prime to B prime? So I need to know basically the coordinates of B prime. I know originally it's 400 in the x, but then to get to B prime, I have to go 405 in the x, or 405I. To get to B prime in the j, I have to go up 300, and then up another 4 to get to B prime. So 304 in the j. And the coordinates of A prime, go 400, and then another 3 in the I direction to get to A prime. And originally it's at 0. I have to go up by 2 to get to A prime, so plus 2j. .405 minus 403 gives me 2i. 304 minus 2 gives me 302j. A prime D prime is going to be easier because D prime is situated at the origin. It's going to be 0i, 0j minus what I just found for A prime, minus 403i plus 2j. So this will be minus 403i minus 2j. Knowing these two vectors, A prime, B prime, A prime, D prime, now I can go back up into equation 2. Remember, how do we do a dot product? If we know the vectors, just what's the procedure we take? We multiply the like components together and add and take the sum of that. In this case, we only have I and j components, but you can do it with k, and if you have four-dimensional things, it would work the same way. So the dot product is going to be 2 times negative 403 plus 302 times negative 2. So this does turn out to be a negative product. This also turns out to be a negative product. So my left-hand side here, I get negative 1410. And it's a scalar, a dot product. You take two vectors, and it gives you a scalar in the end. So negative 1410. And my right-hand side, I have to take the magnitude of A prime B prime times the magnitude of A prime D prime. I have to take the magnitude of this, which will be the square root of 2 squared plus 302 squared, times the square root of 403 squared times 2 squared. That gives me 1.27 times 10 to the 5th. And for right now, I'll carry cosine theta prime A. I have my left side, I have my right side. The only thing I don't know is theta prime A. I can divide both sides by the 1.27 times 10 to the 5th, and I can take the arc cosine of that. This is kind of the one time I will say do keep more significant figures than I normally encourage you to, because the strains, the differences are usually very, very small. So if you don't keep enough sig figs, you're going to find out that the strains turn out to be like 0. So for this one, I did keep 4 digits. I get 90.66 degrees, but I do want this in radians. That is 1.582 radians. That's the new angle between A prime B prime and A prime D prime. The last step is I want the shear strain, and I go back up to my original equation number 1. The shear strain is pi over 2, their original orientation, minus the new angle between them. So I find that the shear strain is pi over 2 minus 1.582, or a negative 0.0112 radians.